transformations.
Not like about driving in the snow today.
And the idea, the point of stress transformations is given a stress tensor in coordinate system A, find that stress tensor in coordinate system B. There are a lot of reasons that you would want to do this, but the most important one is this is, like, we have to do this to find the principal stresses. So the best reason is this is needed to find principal stresses. And then you're like, what's a principal stress? I know you guys. No.
Like driving in the snow and all the other classes are canceled.
No.
In January.
And principal stress. No, listen, I'm going to tell you. No. Right. Principal stress is used for, finding the maximum normals and shear stresses at a point. And these are important for predicting failure. So this idea is really important for being able to guess under what loading conditions a fracture is going to start at a point. So this also predicts failure. Okay, so what makes a vector a vector? And a tensor a tensor? And a tensor a what? Oh, yeah. A tensor. I was trying to think of a tensor. Yeah. I bet that happens to you a lot. So what defines a vector or a tensor is you don't have to take measurements in different, so let's see. Let's say you can predict the measurements in different coordinate systems. By applying a coordinate system transformation. Okay, so I've mentioned this before, and it's kind of a loose idea. I mean, the way I've talked about it is sort of a loose idea, but the idea is for something that's not a vector or a tensor, if you want to know what the measurements are going to say in a specific coordinate system, you have to go to that coordinate system and take the measurements. But if your measurement is a vector quantity or a tensor quantity, you can take that measurement in any coordinate system you want and then apply a coordinate system transformation. So that's the thing. The coordinate system transformation idea is fundamental to what a vector is and what a tensor is. Let's see how it works with vectors first, and then after that I'll go to the extend it to tensors. So a coordinate system transformation goes like this. A vector u expressed in, I'm going to use that sort of relative notation, so vector u relative to a new coordinate system is equal to a rotation matrix Q times the vector relative to the old coordinate system, where this is a rotation matrix. And so, as an example, let's say we have a vector with a length of 10 that makes an angle of 30 degrees above horizontal. In this coordinate system, that vector would be 8.66 for x, 5 for y, 0 for z. Well, if we have a rotation matrix, and I'm not going to go into how to do this yet, but in a few minutes I will. So if we have a rotation matrix that says cosine of 30, sine of 30, 0, negative sine of 30, cosine of 30, 0, 0, 0, 1. Calculate that out and you get the elements 0.866, 0.5, 0, negative 0.5, 0.866, 0, 0, 0, 1. Yes, those are those, just decimals. Yes. Okay, so now, well, let's say, so this is the rotation matrix that takes things in this coordinate system and transforms them to this coordinate system, where this angle is 30 degrees. Okay, so if we have this vector and we want to express its components in this coordinate system, right? What we had before was in the standard coordinate system. But now we're going to figure out what that is in a coordinate system where x is right in line with that. Just by inspection, what are those components going to be equal to? Yeah, 10, 0, 0, because it's all along the x axis. Okay. And so hopefully applying this transformation matrix is going to give us the same thing. So if we take 0.866, 0.50, negative 0.5, 0.866, 0, 0, 0, 1, and multiply that by our original vector in the old coordinate system. So that was 8.6650. You get 7.5 plus 2.5 for the x component. Then you get negative 4.33 plus 4.33 for the y component. Then you get 0 for the z component. That gives you 10, 0, 0. Okay, so that's how the rotation matrix works with vectors. So how do you get the rotation matrix? Well, there's a general description. This isn't really the one that we're going to use most often, but when you're doing 3D calculations, this is a useful way to think about it. No, let me change the thing there. If you have a vector in coordinate system A and want it in coordinate system B, the columns of the rotation matrix, I'm going to call it Q, are the coordinate system axes of A expressed in coordinate system B. This is easy to remember because it's like A, B, A, B, but it's not as easy to make sense out of what that means. But let me go up to this example and we'll think about it. So what we have here is the coordinate system transformation, the rotation matrix. It starts out with vectors in this coordinate system, and after you apply it, represents that vector in this coordinate system. Okay. And the way you do that is, one by one, you take each axis in this coordinate system and express it as a vector in this coordinate system. Okay. So we'll start with the x-axis here and express it in this coordinate system. So now we're just thinking of this vector. This is a vector with a length of 1. What would its components be in this coordinate system? Well, it would have a long component in the positive x direction, right? We're expressing this coordinate system, for this axis in this coordinate system, right? So it would be long in the positive x, so that component's going to be 0.866. It would be short in the negative y, so that component's going to be negative 0.5. Nothing in z, because we're not even dealing with that. And so the first column of the rotation matrix is 0.866, negative 0.50. Okay. Now for the second column, we want to express this vector in this coordinate system. Okay, so it's going to be a small positive x component, so that's going to be positive 0.5. It's going to be a big positive y component, so that's going to be 0.866, no z. So we got 0.5, 0.8660. And then the z-axis stays just the same. You know, it was here before, it's here after. So that's just going to be 0, 0, 1. So that's the general definition. But if your rotation matrix is just making changes about individual coordinate axes, then I can give you just formulas for those. So I'll say for us, these are the things that we're going to do. To rotate the coordinate system, an angle theta about a coordinate system axis and a positive angle and a negative angle are determined by the right-hand rule. So first, if you're rotating about the x-axis, the rotation matrix is 1, 0, 0, 0, cosine theta, sine theta, 0, negative sine theta, cosine theta. To rotate about the y-axis, this is cosine theta, 0, negative sine theta, 0, 1, 0, sine theta, 0, cosine theta. Then to rotate about the z-axis, q is equal to cosine theta, sine theta, 0, negative sine theta, cosine theta, 0, 0, 0, 1. So notice that z and x follow like an identical sort of pattern. The row and column corresponding to whatever axis you're rotating about is zeros and ones, right? We're rotating about x. So here we have a 1 at x, zeros everywhere else in that row and column. And then in the 4 that are left over, cosine, sine, negative sine, cosine. Okay, that's how it works for x. That's how it works for z. We got a 1 and zeros, then cosine, sine, negative sine, cosine. And for y, it's kind of doing the same thing, but it's always got to be a little bit different, you know?
Why?
Y, yeah. Y is always just, it always has to, like, it thinks it's just a little bit special in everything. Yeah, Y always thinks it's so cool.
Is there a mathematical reason?
It is all related to the cross product definitions of the axes up for a right-handed coordinate system. So x cross y is z, y cross z is x, but x cross z is negative y.
Oh,
Yeah, yeah, it's all the answers are there in your right hand. Yeah. Yeah, that's the danger on a test. Oh yeah, and you're like, oh, that guy's screwed. Yeah. Yeah. Um, yeah, right. That kid is like the y-axis of kids. Like he's got to find his own. Yeah, that's what someone else in my class was like. Yeah, well, I use my left hand and I hold my thumb like that. Yeah, that's what you should do. Yeah. Okay, so well, let's do an example where you can see how these sort of relate to each other. Um, find the rotation matrix that takes. So let's say we'll start with the standard coordinate system and re-express the vector in a coordinate system like this: x, y, and then so z is the same. So this rotation is positive 90 degrees about the z-axis. And we're going to do it two ways, using that sort of general definition, A, B, A, B. I don't know that. You know, the thing where like, so to go from coordinate system A to coordinate system B, express the axes for A in coordinate system B. And then we'll also do it, using the cosine and sine approach. All right, well, for the first way, we want to express these coordinate axes in this coordinate system. So a vector like this, what would that be over here? 1. I think you already went wrong on that.
0, negative 1, 0.
0, negative 1, 0, right. So
what was the question?
Just express this vector in this coordinate system.
Oh.
So 0, negative 1, 0. So 0, negative 1, 0. It's going up. This, because we're taking this vector and expressing it over here.
Oh.
So it's 0x and it's in the negative y direction.
Yeah.
And then 0z.
So it's like the magnitude of x in the y vector.
Yeah, just each one of these coordinate axes is a vector, a unit vector. And we're just going to take that unit vector and figure out what its components are using this as a coordinate system. So this one has 0x, -1y, 0z. And then now we'll do the same for y. So this vector, what's that over here? 1, 0, 0, yep. So the second column is 1, 0, 0. And then this is a rotation about z, so that has to stay the same. So 0, 0, 1. Notice that's not a symmetric matrix, by the way. So now we'll do it the other way. And it better give the same thing. Okay, so we're rotating plus 90 degrees about z. So the formula for that is cosine theta sine theta 0, negative sine theta cosine theta 0, 0, 0, 1. So if theta is plus 90, we got 0, negative 1, 0, 1, 0, 0, 0, 0, 1. Yes. Amazing fact. It's its own color. It's so amazing. It doesn't even need any help. Rotation matrices are orthogonal matrices. I don't even remember what that means. I suppose it probably means that the columns of the matrix are perpendicular vectors to each other. But also, oh. Okay, yeah. It definitely has something to do with the columns and or the rows being perpendicular to each other. You don't need to know that because I don't even know that.
But it's an amazing fact.
No, that's not it.
That we don't need to know.
No. The group that it's part of are orthogonal matrices, and what that means to us is that for any orthogonal matrix Q, Q transpose is Q inverse. So if you have two coordinate systems and you go from one to the other one with the rotation matrix Q, then you go from the second one back to the first one using the rotation matrix Q transpose. Okay, so now, in the programs that are on D2L, it tells you how to set up a program that does rotation matrices. You'll probably want to do that. It's sort of a pain to have to type in all those values each time. So let me know when you try to do that if you need help getting that to work. Now we can talk about, the final thing that we've been trying to get to is how do you use these as coordinate system transformations for tensors. We've done it for vectors. So a coordinate system transformation for tensors if let's say a vector in the B coordinate system is equal to Q times a vector in the A coordinate system. Okay, so what that means is if rotation matrix Q transforms from A to B, then a tensor expressed in the B coordinate system is equal to Q times the tensor expressed in the A coordinate system times Q transpose. So to do transformations with tensors, you need the rotation matrix and its transpose. Why do you need that? I was afraid you would ask that.
Don't be.
So why do you need Q and Q transpose? One of them, you can think of it as it reorients the stress cube, the faces of the stress cube. And the other one transforms the traction on each face. So if you think about it, a single rotation matrix would just express, so like a stress cube. Let me draw it. I'll do a simple one. So say that the stress cube is like this, okay? Well, if you applied a single rotation matrix to that, all it would do is re-express this in a new coordinate system. That's not all that's happening. What happens when to express a stress in a new coordinate system is not only that you express this traction vector in a new coordinate system, but that traction also has to be the traction on a reoriented face. Can you picture what I mean? Because you're rotating this whole cube, okay? And so you could think of it as the equation that says the traction is equal to the stress times the normal. You have one of those rotation matrices that does that to rotate all the faces, and then you have another one that re-expresses the traction on each of those faces in what is now our new coordinate system. You don't have to know that, but if you're interested, that's where it's at, man.
What would be
A rotation matrix at all?
no,
Or
both of those transforms, like the traction matrix?
well, that's just so really the use for us is we want to be able to re-express stress tensors in different coordinate systems. To do that, to do it for a vector, you just need one of these. So the question is just why do we have like these two different rotations going on? And the answer is that one of those rotation matrices reorients our stress cube, and one of them re-expresses the vector fraction on each.
A better question would be, where would I see that in normal everyday work? Like, where would I apply this?
The main thing is going to be for calculating the principal stresses. And we haven't done that yet, but we're doing that like next, soon, probably next class. But just like you know, in order to do any kind of matrix calculations, you need to have everything expressed in the same coordinate system. I mean, so a lot of the answers are the same answers it would be for vectors. Like, when would you ever need to express a vector in a new coordinate system? Well, if you have other vectors that are in this other coordinate system and you need to do calculations, you're going to have to transform one or the other, and it's sort of the same here. Yes. Yeah, sure.
Okay, so basically this is kind of like, I mean, if we just had the vector and we wanted to for stresses at that point, then like, it seems like there are several ways you could figure out how to interact with the coordinate system. Either you could write a new parametric vector surface for the surface that's interacting with.
Yeah, well, for us, one of the earlier things that we did was we said, no matter how the face is oriented, the tractions on that face are equal to the stress tensor times an outward facing normal vector. And so it's actually, that's an easy calculation, doesn't take any thinking or anything. But yes, yeah, that's right. Yep. Any other questions? Okay, so let me do an example. And actually, let me do okay, so let's say that we have a stress state where all we have is a uniaxial normal stress. Okay, so let's say it's in compression. So the stress here is 5 times 10 to the 7 pascals. We also have the obscured face, you know, a compressive fraction. And we want to know, so this is in a coordinate system like this. We want to know what this stress is in a coordinate system rotated 45 degrees about the z-axis. X, Y, Z. Okay, well, first, the stress tensor in the, I'll call it the old stress tensor. We have on the x face nothing, so 0, 0, 0. On the y face, we have 0, negative 5 times 10 to the 7th, 0. And then nothing on the z face. Right, so all we have is one normal stress. We don't have any shear stresses. now we have to come up with a rotation matrix to go from this coordinate system to this one. That's a rotation about the z-axis. Is that positive 45 or negative 45? Positive, yep. And so the rotation matrix is cosine of 45, sine of 45, 0, negative sine of 45, cosine of 45, 0, 0, 0, 1. So in decimals, that's 0.7071, 0.7071, 0, negative 0.7071, positive 0.7071, 0, 0, 0, 1. And then in that new coordinate system, the stress tensor is equal to this. That's the rotation matrix. Times the old stress tensor. Times the transpose of Q. So now the old rows are now columns. So this would be 0.7071 going across the rows, negative 0.7071, 0, and then 0.7071, 0.7071, 0, 0, 0, 1. And when you do that calculation, does anybody have those programs in their calculator? And or could I use someone's calculator and punch this in? Okay. 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 Negative 2.5. Oh, yeah. E7, negative 2.5. And then here too. That has to be because of symmetry. And then negative 2.5 here. And then 0, 0, 0, 0, 0. Coordinate system, we got a stress tensor with no shear stresses, only one normal stress, right? Like in our new stress cube, it really would be rotated, but that's hard to draw. So now we have 2.5 times 10 to the 7 there, 2.5 times 10 to the 7 there, and then here, oh, those are negative. So here and here, these are also 2.5 times 10 to the 7. Okay, so we went from having no shear stresses to having shear stresses. And it turns out in fact, there's no coordinate system that, well, let's see. There's no coordinate system where the shear stress, or where any shear stress has a bigger magnitude than this. In other words, the maximum shear stress at this point is 2.5 times 10 to the 7 pascals. Okay, so in a state of uniaxial compression, that's what we have here. If you choose a coordinate system that's rotated 45 degrees from that, you see the maximum shear stress that occurs at this point. And that's actually a very practically important fact. It shows up in compression fractures, of brittle materials. Since brittle materials fail much more easily in shear than they do in tension and compression, if you look at an X-ray of a compression fracture of a bone in the leg, so like a leg compression fracture, there's the bone. That's the long axis of the bone. The compression happens this way, right? 45 degrees from that is like this, and that's what you see in a compression fracture. Because it wasn't the normal stresses that caused this to break. It was the shear stresses that caused it to break. And there were no shear stresses bigger than along a face oriented at 45 degrees. Isn't that cool? Go try it on the way home. We probably all will. Actually, now I'm going to feel so bad when that happens. Yeah. So that's right. So the compression, so like what happens is, I guess a lot of times it happens in car accidents where the feet get slammed against the front of and so you get a huge amount of compression, and either your femur or your tibia breaks in compression like that, and it shows up as at a 45-degree angle, very like reliably. In fact, that's what orthopedic surgeons look for, or forensic, what are they called? The forensic scientists who are trying to recreate. If you see a fracture like that oriented 45 degrees from, then you know that happened as a pure compression fracture, as opposed to like a twisting fracture or something. If it was compressed that way, that's right, it would be, but that never happens, I mean, there'd be other, now that I think about it, there'd be other signs of compressing a bone that way, What? Yeah, your bones aren't very strong that way, so the whole thing just powders, I think.
What if you twisted and
I don't know what would happen, but yeah, you would. So we could do that calculation because so if you had, all we have to know is we know that since bone is really brittle, it barely has any ability to deform plastically, before it breaks. So whatever happens is going to show us the plane where the maximum shear stress is. And from that, we don't know how to do it yet, but we can use principal stresses to figure out what to use the fact that that's the maximum shear stress to figure out where the different loads are coming from. So that'd be fun to do that. Let's, each one of you, like, break your leg in some, try to stump the class,
We get an 80 in the class if we do this.
Like, they'll never guess that I jumped off this building while a chicken was pecking my leg.